Hello and welcome back. So as promised, we are going to solve some more examples from this exercise 1.1 based on the basic concepts of set theory, which is nothing but the definition of the set and the membership relation that has been defined on the set. So let's get started. So in the last session we have already discussed question number 1, whether or not the given collections are sets. Let's go further. So question 2 says, I hope you have your books with you. Given a set A, 1, 2, 3, 4, 5, 6. And we are going to see whether or not the given elements are actually members of it. So does 5 belong to A? Yes, it is a member of the set. Does 8 belong to A? No, it does not belong. Does 4 belong to A? Yes. Does 10 belong to A? No. Does 2 belong to A? Yes. Okay, so this is simple. You can also notice it. Now in the next question, there are some sets that are written in the roster form. The sets are written in the set builder form, and we are going to convert that into the roster form, the listing of elements. Okay, so question 3. The first question says a set A consists of all x such that x is an integer and it is bigger equal minus 3 less than 7. So this is the strict inequality and this is a lenient one, minus 3 bigger equal x. So this should be the collection of all integers. So minus 3 is allowed since there is this equality. Then x is bigger than minus 3. So we should move to the right on the number line. Minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6 because 7 is not allowed. So these are the elements of this set. Then the second one is simple. B consists of all x such that x is a natural number less than 6. It is simply 1, 2, 3, 4, 5. The set C says x is a 2-digit natural number such that the sum of its digit is 8. Now this we are going to write. So C is 2-digit natural number such that sum of the digits is 8. Now how can the number 8 can be broken into two parts so that their sum is 8? The first is 1, 7. We cannot include 0 and 8 because we are considering natural numbers. 0 is not allowed there. So 1, 7. With 1, 7 comes 7, 1 also. Then 2, 6 and 6, 2 also. 3, 5 and 5, 3 also, and then 4 plus 4 which is 44, right? So these are the possible sums for 8, 1 plus 7, 2 plus 6, 3 plus 5, 4 plus 4 and in the reverse order. So these are in fact our members. 17, 26, 35, 44, 53, 62 and 71. 2-digit natural numbers. Sum of the 2 digits is 8 in each case. Then comes set D. X is a prime number which is a divisor of 60. So we know how to consider divisors of 60, right? So what are divisors of 60? It is 2 into 30. Then 2 into 2 into 50. So we are considering the prime factorization of it. Then 2 into 2, 15 can be 3 into 5, and that's it. We stop because this is the prime factorization of 60. So what are the prime divisors of 60? Can 30 come into that? No, 30 is not prime. Can 15 come? No, it is not prime. Can 20 come? Can 10 come? No. The only ones which can come are 2, 3, 5, that's it. So though 2 has been repeated 2 times here, it is 2 into 2 into 3 into 5, we are going to list out 2 just once. So repetition we are going to omit. Then E is denoted by set of all letters in the word trigonometry. Again, what are the distinct letters that we have? T, R, I, G, O, N, O already there, so no need to write again. M, E, T already listed, R already listed, Y. So this is the required set. Also remember, in the roster form, order of elements is not important. It doesn't matter actually. So even if you write this as 17, 71, 26, 62, 35, 53 and 44, it is fine. So order doesn't matter. What matters is all the members should satisfy the common property that is there in the description of the set. Okay, let's go to question 4. So there are some sets that are there in the roster form. We are going to convert into the set builder form. Question 4. Okay, so the very first one is, let it denoted by A. Three, 6, 9 and 12. 4 members of this set A. These are nothing but first 4 multiples of 3 or integers starting with 3 with the gap of 3 digits apart. Anything can be there as a description. So simply we say X is a member such that X is equal to 3k for k equal to 1, 2, 3, 4. For k equal to 1 you get 3, for k equal to 2 you get 6, for k equal to 3 you get 9, for k equal to 4 you get 12, that's it. Then consider the fourth one, will denote it by B. Now this set is something different. We haven't seen such set yet. Okay, what is the difference from the previous examples? Here the elements doesn't stop at a point, at a certain stage. In fact, they go on forever and ever and ever. So this continuity is denoted by these 3 dots. So the elements of this set can be 2, 4, 6, 8, 10, 12, 14. So they follow a pattern, but then there is no limit to that pattern. Okay, the numbers are not going to stop. These are in fact positive even integers, right? So excluding 0, all positive even integers can be considered like this. So we can write this as collection of all x such that x is equal to 2n for all natural numbers n. So n is a natural number. For n equal to 1 you get 2, for n equal to 2 you get 4, for n equal to 3 you get 6, for n equal to 100 there is 200 somewhere lying inside the set, because these dots show the continuity of the pattern and also of the elements. So these are all positive even integers. And then comes the set, let's say it is C. The members are given as 1, 4, 9 up to 100. Now here also there are 3 dots, but they are not at the end, they are in the middle. That means the members are going to stop at a certain stage. These dots show the continuity in the pattern. Now what is the pattern? It is 1, 4, 9, this is 100. These are nothing but squares of first 10 natural numbers. 1 can be considered as 1 square, 4 is 2 square, 9 is 3 square, 100 is 10 square. So what's the pattern? These are squares, in fact squares of first 10 natural numbers. So in the set builder form you can say, now we'll use a different letter just for the sake of convenience and variety. Collection of all y's such that y is equal to x square for or we can again use a suffix here xi for x a natural number, I running from 1, 2, 3 up to 10. So I running from 1 to 10 gives you 10 members, x1 square, x2 square, x3 square, x4 square, okay, and who are these x's? They are natural numbers. You can also have the simplified version of it. You can say it is collection of all y's such that y is equal to n square. So no need to introduce one more variable. You can simply say y is n square, where n is 1, 2, 3 up to 10, a natural number. 1 square, 2 square, 3 square gives you the entire list of elements from this set. Okay. Now let's go to question number 5. So question 5 demands that we should list out all the elements from the given sets. Let's do it. Question 1. A is collection of all x such that x is an odd natural number. So x is a natural number, it starts with 1, it is odd, so also it starts with 1 and goes as, again we are going to use these dots to show the continuity, that the set goes on forever and ever and ever. Then comes set B. X is an integer such that x is between -12 to 9/2. Okay. So don't get frightened by this of fraction situation. Okay, what is minus half? Half is 0.5, so it is minus 0.5. 9 by 2 is 4.5. So the x actually lies between these two decimals, and x is an integer. That means it should be bigger than minus 0.5. Minus 0.5 lies between 0 and minus 1 on the left hand side of the number line. So 0 is here, minus 1 is here, and we have positive integers on the right hand side. So minus 0.5 is here, x is bigger than that, so we should move to the right side of the number line, and x is integer, so the very first integer should be 0, then 1, then 2, then 3, and then 4. You can't go to 5 because that is bigger than 4.5, which is 9 by 2. Okay, simple. Then comes the question 3. A set C is given by x is an integer where x square is less equal 4. That means its square is less equal 4. C, the set C. X is an integer and its square is less equal 4. So we know that squares are always non-negative. Now here x square less equal 4 implies taking square roots, x, the modulus of it, the magnitude of x should be less equal to. That means x can be between minus 2 and 2 because a square root has both symbols, positive or negative, though the square is positive. Okay, so x square less equal 4 implies modulus of x is less equal to, after taking square roots on both sides to retain the inequality. So this is x lies between minus 2 and 2. So minus 2 can come because minus 2 square is less equal 4. Then minus 1 because minus 1 square 1 is less equal 4. Then 0, 0 square 0 is less equal 4. 1 square, 2 square, that's it. Can minus 3 come? No, because minus 3 squared is 9, which is not less than 4. Similarly with 3, positive 3 plus 3, square is 9, which is not less than 4. So this is the only situation where the set can match the description. Okay. Then comes x is a month of a year not having 31 days. So the description given is for set E, a month of year not having 31 days. There are 12 months. January starts with 31 days, so not an option. Then February comes. Now I am only going to write the initials. February either has 28 or 29 days as per the requirement of the leap year. Then March has 31 days, so no chance to feature it here. Then comes April. Yes, April has 30 days. Then May has 31 days, so not an option. June 30 days. Then July, August both 31 days. September 30 days, October 31 days, November 30 days, December 31 days. So months that do not have 31 days are only these: February, April, June, September, November. Okay, so that's it. These were the examples from the exercise. Now, what is one thing that we have observed in all the examples that we have seen till now? So what we have observed is description of a set can be given in any manner. There are different sets. They have different methods of representation. though the method of the representation changes, elements of the set never change. They are still the same. In the roster form, order of the elements does not matter. In the set builder form, the elements are so that all of them satisfy a single common property. And based on these descriptions, all these sets have certain number of elements inside them. Now suppose I give you one description of a set as I am going to call it as D, and this is collection of, or you can even say set of, all months having more than 31 days. Collection of all the months having more than 31 days. Now, is this situation possible? First of all, can a month of a year have more than 31 days? We have just now seen there are either 31 days in a month or less than that. 30 in some case, in case of February 28 or 29, but a month can never have more than 31 days. This is how the calendar works. So, this set D in fact has no element to list out, right? So, nothing can fall under this category. So, we can say that such a collection where the situation is just impossible to list down, or elements, no elements can be there which matches the description. Such a set is called an empty set or a null set or a void set. So, null, void or empty. A set which has no element in it. One such situation is here. The notation is simply the curly brackets and no element inside it, or there is a symbol phi, again a Greek letter, so it is written like this, phi, pronounced like this. Some people even say it is a phi, 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 but it is phi. So D is equal to phi. So phi is a notation for empty set. What is an empty set? Empty set is the set which has no elements inside it. So, can you say that for such a set D, June is a member of D? So, if June is a member of D, June must have, the month of June must have more than 31 days as per the description. Is it so? No. June has just 30 days. So, is June a member of D? No. In fact, no one is a member of D. So, the membership relation cannot be defined on this set. Also, Do not get confused with the curly bracket notation and this notation of phi. There is a set like this. What can you say about this set? Is S an empty set? Well, at the first glance, you might say so that yes, it is an empty set because it features phi, but if you look at it carefully, the phi is a member of this set. So, the description can be, this is set of the, so this is collection where empty set is a member of it. So, can S be empty? No. Empty set is a member of it. So, you can say phi belongs to S. Phi is a member of S, right? Suppose if I write something like this, say set T. Can you say that this set is empty just because it features phi? No. In fact, the set T has two members, two elements, out of which one is an empty set and the other is a set containing empty set, S. So, alternatively, you can say something like this, that T is collection of two sets where phi, you can even say D here with respect to this context, and S with respect to this context. So, T is nothing but collection of two sets D and S, where D itself is an empty set because no element can match this description, and S is this set, set containing an empty set. So, this T has two members, in fact, one member empty set is itself, second member set containing empty set, right? So, this clears the concept of an empty set, right? When to call a collection empty. You can come up with more examples on your own. So, impossible situations where no object, no item, no element can match the description, you can say that that collection is always empty. So, there can be empty sets, sets having no elements. Can a set have just a single element? Well, yes. Suppose I give you the description of set as, in the set builder notation, S contains all x such that x is an even prime number. We all know there is just one prime number that is even, which is nothing but 2. So, S is simply 2. So, this contains just a single element, only one member. Such a set is called as singleton set. Set having just one member. So, yes, for a set, as the description varies, the number of elements, the number of members inside that set also varies. Some set can have no element in it, some sets can have just one element in it. Okay. Now we are going to stop for this session, and in the next session we are going to see what all other types can be there for a set depending on the number of members in it. Till then, bye.